नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। दिस इज द 8th डे ऑफ JEE मेंस रिवीजन एंड टुडे वी आर गोइंग टू डिस्कस अबाउट फर्स्ट पार्ट ऑफ थर्मोडायनेमिक्स। इन फर्स्ट पार्ट ऑफ थर्मोडायनेमिक्स वी आर गोइंग टू डिस्कस अबाउट रिलेशन बिटवीन इंटरनल एनर्जी एंड एंथैल्पी। सो लेट अस स्टार्ट our video. Before starting the video, जो लोग इस चैनल पे नए हैं, अगर हमारा चैनल सब्सक्राइब नहीं किया है तो कृपया उसको सब्सक्राइब कर लें। वीडियो देखने के बाद अगर आपको पसंद आता है तो प्लीज उसको लाइक जरूर करें। So we are starting with this relation. An ideal gas participating in any process, change in internal energy is equal to NCV dt and change in enthalpy is equal to NCP dt. This relation is very useful because whenever we are going to solve a problem, this is coming for an ideal gas, and last year they have asked a question based on this concept. So for a fixed amount of an ideal gas, change in internal energy or change in enthalpy only depends on temperature. So let us try to prove this so that we don't have any hesitation while applying this concept. So for any substance, when we are writing that what is the net change in internal energy can be written as a function of volume and temperature when number of moles of the gas is constant. So the net change in internal energy is equal to the partial change in internal energy with respect to volume when temperature is constant into dV plus partial change in internal energy with respect to temperature when volume is constant into dt. For an ideal gas participating in any process, change in internal energy of the ideal gas is total change in potential energy plus total change in kinetic energy. So total change in potential energy is equal to 0 because there is no interactive forces between ideal gas molecules. So when we are compressing and expanding the gas, there is no change in potential energy. And it's not about only interactive potential energy. We are discussing about there is nucleus and electron. So there is electrostatic force of attraction between nucleus and electron. There is electron repulsion. All these interactive energies is not going to vary when we are going to change the volume or pressure or temperature for an ideal gas. So that's why ideal gas participating in any process, the change in potential energy is equal to 0. So net change in internal energy is equal to change in kinetic energy. Kinetic energy of any substance only depends on temperature change. So if temperature is constant, the change in internal energy is equal to 0. So using this concept, if I apply in this form, here there is a partial change in internal energy with respect to volume when temperature is constant. If temperature is constant, we have proved that the change in internal energy of an ideal gas will be 0. So this part is 0. So we can say that change in internal energy is equal to partial change in internal energy with respect to temperature when volume is constant into dt. By using first law of thermodynamics, when volume is constant, expansion compression work is equal to 0. So I can write that du is equal to del qv and del qv is equal to ncv dt. So from here I can write that partial change in internal energy with respect to temperature when volume is constant is equal to n into cv. So if I put here n into cv into dt, so now we have proved that ideal gas participating in any process, we can write that change in internal energy is equal to ncv dt. Same way, enthalpy of any system is a function of pressure and temperature for a fixed amount of the substance. So now if I am writing that net change in enthalpy, we can write partial change in enthalpy with respect to pressure when temperature is constant into dp plus partial change in enthalpy with respect to temperature when pressure is constant into dt. H is equal to U plus PV. So if we want to calculate this first term, partial change in enthalpy with respect to pressure when temperature is constant, I can write that dH upon dt at constant temperature is equal to du upon dt at constant temperature plus d dp of pressure volume energy at constant temperature. So if I simplify, for an ideal gas, PV is equal to nRT. Since moles, R, and temperature, all three are constant, so differentiation of pressure volume energy at constant temperature with respect to pressure is equal to 0. So this term is 0. We have already proved that if temperature is constant, there is no change in internal energy of ideal gas, so the whole term is equal to 0. Same way, we have proved here that net change in enthalpy for an ideal gas is equal to partial change in enthalpy with respect to temperature when pressure is constant into dt. Now, by using first law of thermodynamics, we can write that change in internal energy is equal to exchange of heat energy and exchange of work energy. So this is expansion compression work. So work is equal to minus times of P external into dV. Since pressure is constant, P external is equal to pressure of the system. So we can write that dU is equal to del Qp minus PdV. If I take this minus PdV on left hand side, we can write that dQp is equal to du plus PdV. And du plus PdV when pressure is constant is equal to dH. So enthalpy changes dQp, and dQp is Ncp dt. So change in enthalpy at constant pressure with respect to temperature is equal to N into Cp. So from here, if I put the value, it is equal to N into Cp, Ncp dt. So again, ideal gas participating in any process, the change in enthalpy is equal to Ncp dt. Now, we have already discussed that an ideal gas participating in any process, there is no change in potential energy. So change in internal energy of an ideal gas is equal to change in kinetic energy. There are three types of kinetic energy. So I can write that the change in internal energy of an ideal gas participating in any process is equal to change in translational kinetic energy. For n moles of the gas, translational kinetic energy is equal to N into translational degree of freedom multiplied by contribution of kinetic energy corresponding to 1 translational degree of freedom. This RT by 2 is corresponding to 1 mole. For n mole, we are multiplying here by n. Same way, we can write for rotational kinetic energy and vibrational kinetic energy. In case of vibrational kinetic energy, the contribution per mole of gas molecules is RT. So if I simplify this, the left hand side, we have already proved that ideal gas participating in any process, change in internal energy is equal to Ncv dt. And if I simplify right hand side, Nr is common in all. It can be Nr by 2 is on outside, dt is here outside. So if I simplify left hand side and right hand side, we can cancel N and dt. And on simplification, we are getting that Cv is equal to translational degree of freedom R by 2, rotational degree of freedom R by 2, vibrational degree of freedom R. This is the formula which is valid under all conditions, right? So from this formula, we can derive the value of Cp, Cv, and gamma for different type of ideal gas. Like suppose our gas is monoatomic. In case of monoatomic gas, there is no rotational and vibrational degree of freedom. So only translational degree of freedom is there. And for any molecule, either it is monoatomic, diatomic, or polyatomic, translational degree of freedom is 3. Translational degree of freedom means movement of center of mass of the molecule. So it can change its 3 coordinates. That's why for any molecule, translational degree of freedom is 3. So from here, if I put the value in this rotational degree of freedom and vibrational degree of freedom is 0. Translational degree of freedom is equal to 3. So Cv is equal to 3R by 2 for monoatomic gas. If I know Cv, I know Cp is 5R by 2, gamma is 5 by 3, that is 1.66 or 1.67. For diatomic gas under normal conditions, in case of diatomic gas is always a linear gas. For linear gas, the rotational degree of freedom is 2. For non-linear gas, the rotational degree of freedom is 3. So from here, if I put the value, I can calculate that Cv is equal to 5R by 2 for diatomic gas under normal condition. If I have to calculate the value of Cv under drastic condition means when vibrational degree of freedom is also active. In order to calculate vibrational degree of freedom, we are writing that the total degree of freedom in a molecule is 3n, where n is the number of atoms. Because each atom has 3 degree of freedom. It has 3 coordinates, right? So that freedom is related to x, y, and z coordinate. Each atom can change its all coordinates. So total degree of freedom is 3n. So from there, the total degree of freedom in diatomic molecule is 6. 3 into 2. 2 is the number of atoms, so 6. So we can calculate that translational degree of freedom is 3. In linear molecule, rotational is 2. So total translational plus rotational is 5. So if I calculate that, what is vibrational degree of freedom? Vibrational degree of freedom is equal to total degree of freedom minus 5, which is 6 minus 5 is equal to 1. So using that, I can calculate that the value of Cv is equal to 5r by 2 plus r, that is equal to 7r by 2. For triatomic non-linear gas, under normal conditions, Cv is equal to only translational and rotational degree of freedom is active. So we can write 3r by 2 plus 3r by 2, that is 3r. Cp is 4r and gamma is 4 by 3, that is 1.33. For triatomic non-linear gas molecules, under drastic conditions, Cv is equal to 5r by 2 plus 3r by 2 plus vibrational degree of freedom into r. So if I want to calculate that, what is vibrational degree of freedom for a non-linear triatomic molecule, we know that total degree of freedom is 9 and translational and rotational degree of freedom is 6. So from here we can write that 9 minus 6 is equal to 3. So Cv value is equal to 6r. There is a question in JEE Advanced, long back they have asked a question that for hydrogen gas at low temperature, Cv value is 3r by 2. On further increasing the temperature, it becomes 5r by 2. On further increasing the temperature, it becomes 7r by 2. On further increasing the temperature, it becomes 3r by 2 again. Explain in 2 and 3 lines. It was a subjective question. So it's simple to explain now that at low temperature, only translational degree of freedom is active. So for hydrogen molecule, the Cv value is equal to 3r by 2. As we increase the temperature near about room temperature, translational and rotational both will be active. So Cv is 5r by 2. Then again, if we increase the temperature, then under high temperature conditions, all three will active. So Cv will be 7r by 2. And on further increasing the temperature, the bond between hydrogen will break. And because of that, now the molecule will behave like a monoatomic gas. For monoatomic gas, Cv value is equal to 3r by 2. Now, the second point is relation between enthalpy and internal energy and pressure volume energy. For any substance, this formula is valid. So total change in enthalpy is equal to total change in internal energy plus total change in pressure volume energy. This is valid for all closed systems, right? So one by one, we have to take examples so that there should not be any confusion while applying this formula. Like there are many formulas for chemical reactions. We are writing that delta H is equal to delta U plus delta NGRT. So we should clear that. When we have to apply, is it always valid or it is conditional? We should know about that. We are also writing that delta H is equal to delta U plus NR delta T. So when we are writing delta H is equal to delta U plus NR delta T, and we should be careful that we cannot write change in pressure volume energy is equal to NR delta T or delta NGRT for solid and liquid. We can always write this change in pressure volume energy is either NR delta T or delta NGRT when the gas is ideal gas. We cannot write when it is a real gas, it is a solid and liquid. So the purpose of discussing this topic is you should be confident that when to use this formula. So let us start with one example. This is an example asked in JEE Advanced. बहुत साल पहले ये example पूछा गया था, तो मेंस के लिए now it's a proper question. So let us discuss this question. 1 mole of liquid at 1 bar and 100 ml. So this 1 bar is the initial pressure of atmosphere on this liquid, right? It is atmospheric pressure or external pressure acting on this liquid when the liquid has a volume of 100 ml is taken in an adiabatic container and the pressure increases steeply to 100 bar. So अचानक इस liquid के ऊपर pressure 100 bar change कर दिया गया. Then at a constant pressure of 100 bar, volume decreases by 1 ml. So if we keep the pressure constant for some time, then after some time the volume is decreased by 1 ml. Find delta U and delta H for this process. Whenever we are going to solve question about change in internal energy and enthalpy, they are a state variable. So what is the benefit of a state variable? That you can follow any path. If initial and final state will be same, the change in that state variable will be same. Either it is Gibbs free energy, it is internal energy, enthalpy, entropy. We are using this concept again and again in thermodynamics as well as thermochemistry. So let us try to solve this question. मैं ये कह सकता हूँ कि इस क्वेश्चन में सिस्टम 3 स्टेट्स को गेन कर रहा है. एक स्टेट इनिशियल स्टेट है, एक अचानक चेंज वाली इंटरमीडिएट स्टेट है और एक फाइनल स्टेट है. सो व्हेन आई एम मूविंग फ्रॉम first state to second state, I can say that since it is in adiabatic container, there is no exchange of heat energy between system and surrounding, and volume of the system is also not changing, so work done is equal to 0. There is no expansion compression work because volume is constant. Using first law of thermodynamics, I can say that change in internal energy for this process from state 1 to state 2 is equal to 0. Same way, if I apply this concept, again this whole thing is taking place in adiabatic container, so Q is equal to 0. When I will calculate the work done, since volume is decreasing, work done will be positive because there is compression of liquid by external pressure. So work done is equal to minus times of P external, V final minus V initial. So when I am writing here P external, since pressure is constant from state 1 to state 3, that is 100 bar, minus times of, in place of P external, I can use this 100 bar. And volume change, volume is decreasing, so volume decreased by 1 ml, minus sign, divided by 1000. I have converted this volume from ml to liter. So if I simplify this, since it is compression, the work done in this process will be 1 by 10 liter bar. And now we can write by using first law of thermodynamics that Q is 0. So delta U in process 2 to 3 is equal to work done in process 2 to 3, that is equal to 1 by 10 liter bar. So the first part is solved. I can say that the net internal energy change for the system from moving from state 1 to state 3 is the sum of change in internal energy from 1 to 2 and 2 to 3. So from there we can write that this value is equal to 1 by 10 liter bar. Now if I have to calculate what is the enthalpy change in the whole process from 1 to 3, I can write that delta H in 1 to 3 process is equal to delta U in process 1 to 3, and then we can write what is the change in pressure volume energy. So pressure at state 3, volume at state 3 minus pressure at state 1, volume at state 1. So this we have already calculated. This value is equal to 1 by 10. Pressure at state 3 is equal to 100 bar and volume is equal to 99 ml. Convert this into liter, divide by 1000. Initial pressure is 1 bar and volume is equal to 100 ml. So 100 divided by 1000. So if I simplify this 1 by 10 and this 1 by 10 will cancel out. On simplification of this, I can say that the change in enthalpy is equal to 9.9 liter bar. So enthalpy change is 9.9 liter bar and internal energy changes 0.1 liter bar. So this is one question where they are asking about liquid relation between internal energy and enthalpy. Let us take another example. This is also very common example and it is also from JEE Advanced. 1 mole of a non-ideal gas undergoes a change of state. So this initial state is given and it is not an ideal gas, right? They have mentioned that this is a real gas. So be careful that when it is a real gas, I cannot say PV is equal to nRT, or we cannot say delta PV is delta nRT, or we can say that delta PV is nR delta T. We cannot use PV is equal to nRT when it is a non-ideal gas. They have given that during this change from state 1 to state 2, the change in internal energy is 30 liter ATM, and they are asking what is the change in enthalpy in liter ATM of the process. So I can write the relation for change in enthalpy is equal to change in internal energy plus change in pressure volume energy. And here I cannot put that is equal to nR delta T because they have mentioned the temperature also and 1 mole of real gas is there, but I cannot use nR delta T because that is valid when the gas is ideal. So be careful about that. Some of the student can make the mistake because temperature is given, moles are given. So what we are going to write here, delta H is equal to delta U, and pressure volume energy initially I can write that is 6 and finally I can write 20. So 20 is PV final minus PV initial, that is equal to 6. So if we simplify, we can write that 30 plus 14 is equal to 44 liter ATM. So very simple, very common question asked in JEE Advanced, right? So again, what we have learned that when we are applying this PV is equal to nRT, if temperature is constant, we are writing that change in pressure volume energy is equal to nR delta NGRT. When the temperature is variable, moles are constant, then we are writing that delta PV is equal to delta Ng into RT. Basically, this delta Ng into RT will use in a chemical reaction. While here, when a ideal gas is subjected to expansion and compression, then we can write that this value is equal to this, here when the gas is participating in some expansion and compression process, then I can write that change in pressure volume energy is equal to nR delta T, right? So we can use this, but we can use only for ideal gas. We cannot use for real gas. So be careful while using these relations because this is a common confusion in students, right? Let us take another example. An liquid is there and it is subjected to adiabatic expansion, and liquid is adiabatic expansion from state 1 to state 2. They have given this state 1 and this is state 2 and there is no graph. So it is sudden process, irreversible process, suddenly by a single step as shown in the figure, right? So it is an irreversible process. Pressure versus volume graph is given and they are asking that what is enthalpy change, what is internal energy change, right? So we have to calculate enthalpy change and internal energy change. So first thing is that since it is in adiabatic container, Q will be 0. First law of thermodynamics is valid for all. So I can write that change in internal energy is equal to work done. Since when we are writing this, work done, since it is irreversible process, when we define work done in irreversible process is equal to minus times of P external V final minus V initial. When some expansion is taking place of this liquid and they have not mentioned that what is the external pressure, it is a common sense that the external pressure is equal to final pressure of the system. So from here, if I calculate that the final pressure of the system is P naught, what is the volume change? 4V naught minus V naught, that is 3V naught. So by using that, we can calculate that what is the change in internal energy of this system. So change in internal energy is minus P naught V naught. And now we can calculate change in enthalpy. I cannot use Cp delta T because that is not ideal gas. It is a liquid. We cannot use those formula. So here when I am writing delta H, I can use that delta H is equal to delta U P2 V2 minus P1 V1. Already we have calculated delta U by using first law of thermodynamics. That value is minus times of P naught into V naught. Now P final, V final, P2 V2 is 4 times of P naught V naught and P1 V1 is 2 times of P naught V naught. So if we simplify, we are getting that the enthalpy change in this process is minus times of P naught V naught. So this is the enthalpy change and this is the internal energy change during the process, right? So by using first law of thermodynamics and keeping that substance system is not gas, it is liquid, we can solve this problem. Now for a chemical reaction, because most of the time when we are using, we should be very confident and clear that whatever we are using is correct or not. So let me discuss for a chemical reaction. For a chemical reaction, Nitrogen in gaseous state plus 3 times of hydrogen in gaseous state will form 2 times of ammonia in gaseous state. So if I am writing this relation, delta H is equal to delta U plus delta times of pressure, volume, energy. We know that chemical reactions taking place in two conditions. If this reaction is taking place at constant volume and constant temperature condition, then volume is constant. So delta of PV, V is outside. So I can write V delta P. And this relation is valid for all substances. If the reaction is taking place at, if it is real gas also, then also it is valid that when volume is constant, then change in pressure, volume, energy is equal to V into delta P. But now if these gases will behave ideally, if the gases are ideal also, then volume into delta P can be written, because this reaction is taking place at constant temperature. Temperature is not changing, volume is constant. So moles are changing, because of that pressure is changing. So pressure is changed because of change in number of moles. So basically when we are writing this relation, we should keep in mind that delta NGRT is not always valid. It is valid when the gases participating in the reaction is ideal gas and temperature is not changing during the chemical reaction, then this formula is going to valid. Same way, if this reaction is taking place at constant pressure and temperature, then we can write that delta H is equal to delta U when pressure is constant. This is P delta V. And now again we can say that if the gases are ideal, if the gases are not ideal, then we cannot use this. If the gases are ideal, then we can write that P delta V is equal to delta Ng RT. So most of us remember the formula that delta H is equal to delta U plus delta Ng RT, but we don't remember that under what condition this formula is valid. So be careful about those things. Delta H is equal to delta U plus delta NGRT is not always valid. It is valid only when this gas is behaving like ideal gas. So let us solve a question again based on relation between enthalpy and internal energy. At 500 kilobar and T Kelvin, the density of graphite and diamonds are 2 and 3 gram per centimeter cube respectively. The value of delta H minus delta U for the conversion of 1 mole of graphite into diamond at 500 kilobar and T Kelvin. So temperature is constant here. So we have to write that what is the difference between change in enthalpy and change in internal energy. We know that is equal to change in pressure, volume, energy. When we are writing this, we know that pressure is constant. So we are using P delta V, but this is not a gas, it is solid. So we cannot write P delta V is delta NGRT, right? So here if I am putting the values of, first we have to calculate that what is the volume change during the process. So we are converting graphite into diamond. When we are converting this graphite into diamond, the density of diamond is more, means volume is less. So here if we write that for 1 mole, because we have to calculate this for 1 mole. If I calculate that what is the volume of graphite initially, so mass of 1 mole of graphite is 12 gram and density is 2. So this volume is equal to 6 ml, because density is in gram per ml. Same way we can calculate what is volume of diamond. So 12 gram divided by density is 3, so volume is 4 ml. So during this process, if I write that what is the volume change is final minus initial, that is equal to minus 2 ml. So that 2 ml can be converted into liters. So 2 divided by 1000 liter. So this is the volume change, or I can write in meter cube, that is minus 2 into, again we divide by 1000. So we can write 2 into 10 to the power minus 6 meter cube. This is the volume change. I have taken meter cube because I have to calculate the answer in joule or kilojoule. That's why I have done that. Now we can write that the value of P delta V, pressure is equal to 500 kilobar. Kilo means 10 to the power 3. And in SI unit, if I put bar, 1 bar means 10 to the power 5 Pascal. So this is the pressure in Pascal. And volume change we have already calculated, minus 2 into 10 to the power minus 6. So if we further simplify, we can write that this value is minus, and 2 into 500 is 1000. And if I further simplify, 10 to the power 8, and this is 10 to the power minus 6, so it is 10 to the power 2. So this value is coming in joule. If I want to convert into kilojoule, this value will be minus 100 kilojoule. Minus 100 kilojoule. So we'll get this as answer, right? So this is very important. So many simple questions, conceptual questions can be based on this concept, relation between enthalpy and internal energy. So most of the question in NCERT and most of the question in JEE mains is related to chemical reaction, relation between delta H and delta U for a chemical reaction. Let us go through this problem. For the reaction, 2 times of carbon monoxide in gaseous state plus O2 in gaseous state will form 2 times of carbon dioxide in gaseous state. Delta H for this reaction is given. In 1 liter vessel at 500 Kelvin, the initial pressure is 70 atm, and after the reaction, the pressure becomes 40 atm. So decrease in pressure is there, and this is taking place at constant volume 1 liter. Calculate the change in internal energy. All the above gases show significant deviation from ideal behavior. Means we cannot write that delta H is equal to delta U plus delta Ncert because temperature is given, so it is tempting, but we cannot use because the gases are not ideal. So what we'll write here, that delta H is equal to delta U plus delta times of pressure volume energy. Pressure is changing, so I can write that volume is constant, volume into change in pressure. So here we can write that delta H value they have given. So first we'll calculate what is the value of V delta P. Volume is 1 liter, and they have given liter atm is 0.1 kilojoule, so we'll convert into that. And pressure change, final minus initial, so pressure change is negative minus 30, so this is in liter atm. If I have to convert into kilojoule, this is minus 3 kilojoule. 0.1 से multiply कर देंगे, this is minus 3 kilojoule. So we got V delta P. Now if I have to calculate what is delta H, delta H is equal to, delta H is already given, so delta H is equal to delta U. Delta U we have to calculate, and we already know that V delta P is minus 3. So from here we can write that delta U is equal to delta H of this reaction is minus 560, and if I take this minus 3 on the left hand side, it will be positive. So this value is equal to minus 557 kilojoule. Right, so calculate the change in internal energy in kilojoule. This is the value, but be careful that since moles we can apply that temperature is given, so be careful because here it is not an ideal gas, so we cannot apply V delta P is NR delta T or delta Ncert, because you can write that what is delta Ng for this reaction. According to balanced reaction, delta Ng will be minus 1. Temperature is given, so it is tempting to write delta Ncert, but don't use because they are saying deviation from ideal behavior. Okay, so I hope that you will not do these type of mistakes. One more example, while writing this relation for a chemical reaction, they have given that consider the reaction is taking place at 300 Kelvin. H2 gas plus Cl2 gas will form 2 HCl gas. Delta H0 for the reaction is minus 185 kilojoule. And here it should be kilojoule per mole, means according to the balance reaction. According to balance means when 1 mole of hydrogen will react with 1 mole of Cl2 to form 2 moles of HCl, then the heat energy liberated at constant pressure is minus 185. So per mole is representing according to balance reaction. Now in this question, if 3 moles of hydrogen completely react with 3 moles of chlorine, so first I have to write that delta H is H2 in plus Cl2 will form 2 times of HCl in gaseous state. Now at time t is equal to 0, they have given that 3 moles of hydrogen and 3 moles of chlorine is there. If they will completely react at any time t, 6 moles of HCl will form. So we can solve this problem in 2 ways. The first way is we have written what is delta H0 of the reaction. Delta H0 of the reaction is minus 185 kilojoule. Now we can write that what is the relation between delta H and delta U. So delta H is equal to delta U. Since not is there, we'll write everywhere not. And since they have not mentioned that the gas is real or ideal, and only temperature is mentioned. There is no mention of pressure, volume, right? Only temperature is mentioned. So that is an indication to assume that the gases participating in this reaction is ideal gas. So we can write delta Ng RT. So if I'm writing according to balance reaction, delta Ng is equal to 0. So from here we can write that for balance reaction, when 1 mole of hydrogen and 1 mole of chlorine is reacting, delta H is equal to delta U naught, and that is equal to minus 185. But here in this particular condition, 1 mole is not reacting, 3 moles are reacting. So if I have to give the final answer should be 3 times of minus 185. 3 times. Some of the student will do this calculation and leave it, right? It is not 1 mole and 1 mole. When 3 and 3 mole are participating, you have to write. Suppose here it is 2 mole and 3 mole, then you have to apply the concept of limiting reagent. Then only 2 moles are participating in the reaction. So you have calculated corresponding to 1 mole, multiply it by 2. So based on the data, you have to solve. Sometimes the data is such that one chemical species limiting reagent. So first you calculate the value of delta U for the balanced chemical reaction. And then you find out who is limiting reagent. And then you multiply by that factor, you will get the answer, right? So these are very simple questions, but you should not do mistake in these type of things. Okay, so till now we have discussed about relation between internal energy and enthalpy. Now we are going to discuss an important topic, entropy. So when we are discussing entropy, there is a common confusion, right? So when we are writing entropy, entropy is derived from Carnot cycle. Since it is derived from Carnot cycle, from there we got the formula that entropy is a state variable. So change in entropy is equal to dq reversible upon T. This formula we have derived from Carnot cycle. This is not valid. ds is not equal to dq irreversible. Suppose now the question is, we have to calculate entropy change in irreversible processes also. So whenever we have to calculate, how to calculate entropy change in irreversible processes? Whenever we have to calculate entropy change, either the process is reversible or irreversible. In order to calculate entropy change, we have to follow a reversible path. For example, suppose here if I am moving from initial state A to initial state B, final state B, through this path, this is a dotted path indicating that this is an irreversible process, because if it is reversible, then it is a curve. We know each and every state. So this is the first path. If I have to calculate what is the entropy change in this irreversible path, then what will do that I can choose any reversible path. I have chosen this reversible path. I will move from here to here and then from here to there, right? So if I can say that if this is C, I will move from A to C and then C to B. And the entropy change in A to C plus C to B is equal to the entropy change in A to B, because entropy is a state variable. Entropy change of this path or this path, it is entropy of B minus entropy of A. So this concept we are going to use whenever we have to calculate the entropy change in irreversible process. So there should not be any confusion. I will try to simplify this. I will try to tell all the concept by which you will feel that there should not be any confusion. So let us take an example. Here we have taken an ideal gas, right? So for an ideal gas, we are saying that ideal gas participating in any process, change in internal energy is NCV dt, change in enthalpy is NCP dt, and change in entropy is equal to NCV ln T2 upon T1 plus NR ln V2 upon V1. So we are going to derive these formula, and we are trying to understand that the process is reversible or irreversible. We can calculate the entropy change in irreversible process by using this formula, right? So we have to make that confidence that we can use this formula blindly, right? So for that, we are taking an example here. Pressure versus volume graph. We are moving from A to B position, right? And this path is irreversible. This dotted path is irreversible, and this path is reversible, right? Since entropy is a state variable, entropy change of this path or that path, that is SB minus SA, so entropy change will be same for both paths. So now I am writing that If an ideal gas participating in a reversible process, I can use this path to calculate entropy change. So ds is equal to dq reversible upon T. For an ideal gas, using first law of thermodynamics, I can write that dq is equal to du plus pdv. So here I have applied first law of thermodynamics. And since process is reversible, according to the definition of reversible process, in reversible process, at each and every point, the difference between external pressure and pressure of the system is almost same. So we can put pressure of the system in place of P external, right? So here, while writing work done, I have written that this is P of the system into dV. So dQ is equal to du plus P dV. And one common error, because you are practicing so many questions in physics, you forget to use the sign convention of chemistry, right? So physics people, when they are calculating that work done, they are following European convention. And according to physics formula, you are not able to calculate the work done when the gas is expanding in vacuum. Because according to physics, when you are calculating that work done is pressure of the system into dV. And pressure of the gas is always positive. So when the gas is expanding in vacuum, this gas pressure is always positive, volume is changing. So according to physics, then this work done should be negative. Okay, you are writing here P plus dV in physics, so it should be positive. But there is no opposing force, right? So gas is not doing work. According to chemistry, you will get the answer. You are writing that this work done is equal to minus times of P external into dV. This is IUPAC convention, and P external is 0. That's why work done is 0. So whatever the formula you are using, it's fine. That formula cannot apply in vacuum, right? You can apply when the external pressure is not non-zero and there is an equilibrium between system and surrounding, then only you can apply, right? For irreversible process, you cannot write. So there are limitations of that, but whatever you are using in physics, I am just saying that don't apply the formula of physics in work done. So that formula is also not valid for work done in expansion compression, right? So here our purpose is not to discuss that. Our purpose is to calculate the entropy change, right? So now I am writing that entropy change is equal to change in internal energy plus change, this work done is PdV. For an ideal gas participating in any process, change in internal energy is NCV dt. So NCV dt upon T. P upon T is equal to NR by V. So NR by V into dV. So if I integrate, I can write that change in internal entropy is equal to NCV ln T2 upon T1 plus NR ln V2 upon V1. And for an ideal gas, PV is equal to nRT is always valid. So we have already discussed that we can use this in gaseous state. V2 upon V1, because moles are not changing, is equal to T2 upon T1 into P1 upon P2. If I put here in place of V2 upon V1, I will get the second formula. And in the second formula, if I put the value of T2 upon T1, I will get the third formula, right? So either you remember any one of them, right? With practice, you can remember all the three. But if you remember one of them, with the help of that, you can derive. So we are focusing on one. We can say that ideal gas participating in any process, entropy change is equal to NCV ln T2 upon T1 plus NR ln V2 upon V1. So let us try to understand that if the process is A to C, it is an irreversible process. I have taken pressure versus volume graph for an ideal gas participating in A to C process, which is adiabatic irreversible process. Suppose I have to calculate entropy change in this process, right? So most of the students who don't understand the concept of entropy change, they confuse that in adiabatic process, Q is 0. Q irreversible is 0. When the same process is carried out reversibly, Q is not 0. That's why in adiabatic irreversible process, entropy change will be positive for system. Q irreversible is 0. When the same process, I will move from A to C position by some reversible path, Q of this path is not equal to 0. So Q reversible is positive, temperature in Kelvin is positive. That's why entropy change from A to C for an ideal gas will be positive. So try to understand that. Let us prove it so that confidence will come. So here we are saying that initial and final state is same. This is the first path, which is adiabatic irreversible. This is the second path, which is adiabatic irreversible. Entropy change in both paths should be same because initial and final state is same. So entropy change in AC is equal to entropy change in AB plus entropy change in BC. Entropy change in AB is 0 because it is adiabatic reversible. So Q reversible is equal to 0. So this is equal to 0. So entropy change in process A to C is equal to entropy change in process B to C. So I want to prove that this is irreversible process A to C. And if with the help of reversible process, if I derive the formula, I will get the same formula what we are using. अभी हमने ये पढ़ा कि कैसा भी प्रोसेस हो, वी कैन अप्लाई द फॉर्मूला NCV ln T2 upon T1 NR. सो इट इज इरिवर्सिबल. मैं उस फॉर्मूले को यूज कर रहा हूँ कि A से C प्रोसेस में ये फॉर्मूला वैलिड है, राइट. अब मैं इसको प्रूव करने वाला हूँ कि ये क्यों वैलिड है. वी आर गोइंग टू प्रूव दैट व्हाई इट इज वैलिड, राइट. सो फॉर दैट व्हाट वी आर डूइंग दैट वी आर मूविंग फ्रॉम A टू B. अगर हम A से B मूव करेंगे तो हम एंट्रोपी चेंज लिखेंगे A से B प्रोसेस में NCV ln फाइनल टेम्परेचर TB, इनिशियल इज TA, NCV ln TB अपॉन TA प्लस NR ln VB अपॉन VA. और B से C जाएंगे. B से C में क्या है, वॉल्यूम इज कांस्टेंट. So second term will be 0. So we can write NCV temperature at point C point divided by temperature of B point. NCV ln TC upon TB. अगर हम इन दोनों को जोड़ दें तो NCV is common. TB and TB will cancel out. So we can write NCV TC upon TA or NR VB upon VA. Since VB and VC are equal, in place of VB I can write VC. तो अभी ये फॉर्मूला आ गया जो हमने यहाँ पे ये भरोसा करके लगाया था कि ये तो इरिवर्सिबल प्रोसेस है, लेकिन मुझे अगर इनिशियल एंड फाइनल दो टेम्परेचर और इनिशियल एंड फाइनल दो वॉल्यूम पता है तो मैं ये फॉर्मूला यूज कर सकता हूँ. तो आई हैव प्रूव्ड यू दैट you can have faith and apply the formula blindly, right? This is valid, either the process is reversible or irreversible. एक और एग्जांपल लेके चलते हैं इस बात को प्रूव करने के लिए. मुझे A से B जाना है, ये पाथ 1 है, प्रेशर वर्सेस वॉल्यूम ग्राफ है, आइडियल गैस की बात हो रही है, और दिस प्रोसेस इज इरिवर्सिबल. अगर इरिवर्सिबल प्रोसेस, मुझे पता नहीं कि कैसा प्रोसेस है ये, बट मुझे एंट्रोपी चेंज कैलकुलेट करना. आई विल मूव फ्रॉम A टू C रिवर्सिबली एंड देन C टू B. A से C आइसोबेरिक है और C से B जो है वो आइसोकोरिक है. सो आई एम राइटिंग दैट एंट्रोपी चेंज इन प्रोसेस A टू B इज एंट्रोपी चेंज इन AC, एंट्रोपी चेंज इन BC. अब अगर मैं इंट्रोपी चेंज इन ए बी ये सोच के कि रिवर्सिबल हो या रिवर्सिबल हो, फॉर्मूला वैलिड है. NCV ln TB अपॉन TA प्लस NR ln VB अपॉन VA. ये फॉर्मूले से बेस मैंने डायरेक्ट लिख दिया. अब ये वैल्यू क्यों आएगी, हम इसको डिस्कस कर रहे हैं कि ये सही क्यों है. सो व्हाट वी आर डूइंग दैट, वी आर टेकिंग अ रिवर्सिबल पाथ, वी आर मूविंग फ्रॉम A टू C. A से C वाला पाथ आइसोबेरिक है, तो आइसोबेरिक पाथ में क्या होगा, dqp upon T. dqp is ncp dt, ncp dt upon T, so that is ncp ln final temperature is C, initial temperature is A. And same way for C to B, C से B वाला process isocoric है, so dqv upon T. So dqv is ncv dt, ncv dt upon T को integrate करेंगे तो ncv ln final temperature is TB, initial temperature is TC. So now if I simplify, मैं Cp को लिख सकता हूं Cv plus R, and if I expand this, then this value is equal to NCV ln TB and TC. Okay, so here when we are writing this value, NCV ln TC upon okay, right, yes, NCV ln TC upon TA, and this is NCV ln TB upon TC. So this TC will cancel out and we'll get that NCV ln TB upon TA. And NR ln TC upon TA is there, NR ln TC upon TA. And since C and A process की अगर मैं बात करूं तो process is isobaric. When pressure is constant, temperature ratio is volume ratio. So TC upon TA is VB upon VA. So we are getting the same formula, right? We have proved 2 times. So we don't have any hesitation while applying the formula. Either the process is reversible or irreversible. If we know 2 volumes and 2 temperatures of initial and final state, 2 pressure and 2 volume of initial and final state, two pressure and two temperature of initial and final state, we can apply these formula to calculate entropy change. Now entropy change of universe, हमें मालूम है कि यूनिवर्स जो है वो सिस्टम और सराउंडिंग से बना है, तो वी कैन से दैट टोटल एंट्रोपी चेंज और एंट्रोपी चेंज ऑफ यूनिवर्स इज एंट्रोपी चेंज ऑफ सिस्टम प्लस एंट्रोपी चेंज ऑफ सराउंडिंग. एंट्रोपी चेंज ऑफ सराउंडिंग, वी नो दैट कि अगर हम पूरे यूनिवर्स को एक रेक्टेंगल से रिप्रेजेंट करें, इफ दिस इज रिप्रेजेंटिंग अ रेक्टेंगल, then the part of our system in this universe is very small. Anything except system in the universe is surrounding, means surrounding is very large. You cannot change the pressure and temperature of the surrounding. और कोई चीज सराउंडिंग के रिस्पेक्ट में हमेशा स्लो होगी, क्योंकि ये बहुत बड़ा, अगर सिस्टम ने जल्दी से हीट एनर्जी रिलीज करी या एब्जॉर्ब करी, लेकिन सराउंडिंग के रिस्पेक्ट में वो स्लो प्रोसेस ही होगा. इस वजह से whenever we have to calculate entropy change of the surrounding, we can directly apply q surrounding upon t. इधर नहीं सोचना है कि प्रोसेस रिवर्सिबल है या इरिवर्सिबल है. with respect to surrounding, it is always reversible, right? So this formula is always valid and we cannot change the temperature and pressure of the surrounding. The third point is, अगर प्रोसेस रिवर्सिबल है, ये क्लाउसियस इनइक्वालिटी से हम प्रूव करते हैं, अभी हम प्रूव नहीं करने जा रहे, डायरेक्ट यूज करने जा रहे हैं कि अगर प्रोसेस रिवर्सिबल है तो यूनिवर्स की एंट्रोपी चेंज नहीं होगी, और अगर प्रोसेस इरिवर्सिबल है तो एंट्रोपी ऑफ यूनिवर्स विल इंक्रीज. वी आर यूजिंग दिस कॉन्सेप्ट्स टू सॉल्व, टू सिंप्लीफाई क्वेश्चंस, राइट? Fourth point is, in any adiabatic process, either the process is reversible or irreversible. एडियाबैटिक प्रोसेस कैसा भी हो, सिस्टम और सराउंडिंग के बीच में हीट एनर्जी का एक्सचेंज नहीं होगा. तो जब भी हमें डेल्टा एस सराउंडिंग निकालना है, क्यू सराउंडिंग इज ऑलवेज जीरो इन एडियाबैटिक प्रोसेस, सो दिस इज इक्वल टू जीरो. बट एंट्रोपी चेंज ऑफ द सिस्टम can be zero or cannot be zero. When the process is reversible, then entropy change of the system will be zero. And under this condition, we'll say that adiabatic reversible process जो होता है, adiabatic reversible process is also known as isoentropic process, because entropy of system, surrounding and universe is not going to change. Entropy is constant, isoentropic process. But when the process is adiabatic and irreversible, then the entropy of the system is going to increase, but there is no change in entropy of the surrounding. This is adiabatic irreversible. क्योंकि हम कह रहे हैं इरिवर्सिबल में यूनिवर्स की एंट्रोपी बढ़ेगी, सराउंडिंग की चेंज नहीं हो रही, कैसे बढ़ेगी? सिस्टम की एंट्रोपी बढ़ेगी. तो दुनिया में ऐसा कोई भी एडियाबैटिक प्रोसेस नहीं है जिसमें सिस्टम की एंट्रोपी कम होती है. एडियाबैटिक में या तो एंट्रोपी चेंज नहीं होती है, एंट्रोपी बढ़ती है. देयर इज नो प्रोसेस इन विच, एडियाबैटिक प्रोसेस इन विच एंट्रोपी ऑफ सिस्टम इज गोइंग टू डिक्रीज. एंट्रोपी चेंज ड्यूरिंग फेज ट्रांजिशन. तो पहली चीज, व्हाट इज फेज ट्रांजिशन? व्हेनेवर वी आर टॉकिंग अबाउट फेज ट्रांजिशन, फॉर्मूला शुड नॉट चेंज. फॉर्मूला ऑन द लेफ्ट हैंड साइड एंड फॉर्मूला ऑन द राइट हैंड साइड शुड बी सेम. तो ये फेज ट्रांजिशन है. H2 इन सॉलिड स्टेट इज, इसको हम मेल्टिंग भी कहते हैं. तो when melting is taking place at its melting point, because we know that when pressure is 1 atm and temperature is 273.15 Kelvin, अगर हम प्रेशर वर्सेस टेम्परेचर ग्राफ वाटर के लिए ड्रॉ करें, तो ये जो है ये लाइन पे अगर कोई पॉइंट एग्जिस्ट कर रहा है, मींस there is an equilibrium between solid state and liquid state, right? So there are infinite point on this line, right? So there are infinite condition where there is an equilibrium between solid and liquid. तो एक solid और liquid का equilibrium means melting point. तो एक substance के infinite number of melting point हो सकते हैं. If you change the pressure, melting temperature will change. So here what we are discussing that कि यहाँ पे जब हम normal conditions में melting point पे melt कर रहे हैं, so there is an equilibrium between solid and liquid state, and pressure and temperature is also constant here, right? So when we use Gibbs free energy, we are writing delta G of the process is equal to delta H minus T delta S. At equilibrium, delta G is equal to 0. So from there I can write that entropy change of this is equal to enthalpy change of the process divided by temperature. और जब आइस मेल्ट होगा, प्योर सब्सटेंस से मेल्ट होगा, तो टेम्परेचर भी चेंज नहीं होगा, प्रेशर भी चेंज नहीं हो रहा, टेम्परेचर प्रेशर इज कांस्टेंट. सो आई कैन से दैट डेल्टा एस फ्यूजन इज इक्वल टू डेल्टा एच फ्यूजन डिवाइडेड बाय टेम्परेचर. या एक दूसरा तरीका मैं ये कह सकता हूँ कि इंट्रोपी चेंज मुझे निकालना है, स्मॉल चेंज के लिए लिखा डीएस, डीएस इज इक्वल टू डी क्यू रिवर्सिबल अपॉन टेम्परेचर. डी क्यू रिवर्सिबल, प्रेशर कांस्टेंट है इस प्रोसेस में, तो आई कैन राइट दैट डी क्यू रिवर्सिबल को अगर प्रेशर कांस्टेंट है तो डीएच लिख सकता हूं, तो डीएच अपॉन टी, और फिर इंटीग्रेट कर दिया और ये फॉर्मूला आ जाएगा. तो दोनों ही वैलिड हैं. तो जब क्वेश्चन पूछा जाएगा तो आप ये देखोगे कि मेल्टिंग मेल्टिंग कंडीशंस में हो रही है क्या, अगर हो रही है तो इंट्रोपी चेंज का ये फॉर्मूला हम लगा सकते हैं. ये तो फर्स्ट पॉइंट हो गया. एट पॉइंट ए वी आर डिस्कसिंग, तो मैं लिख सकता हूं कि पॉइंट ए पे इंट्रोपी का चेंज जो होगा दैट इज इक्वल टू एंथैल्पी चेंज डिवाइडेड बाय मेल्टिंग टेम्परेचर. नाउ वी आर डिस्कसिंग एट पॉइंट बी. पॉइंट बी पे हम मेल्टिंग डिस्कस कर रहे हैं. प्रेशर 1 atm है लेकिन रूम टेम्परेचर है, एंड रूम टेम्परेचर पे फ्रॉम दिस ग्राफ आई कैन से दैट लिक्विड स्टेट इज स्टेबल. तो अगर मैं इस बी जगह पे अगर मैं सॉलिड आइस को लेके आऊंगा तो सॉलिड आइस अनस्टेबल है, अपने आप वो लिक्विड में कन्वर्ट हो जाएगा. अपने आप हो रहा है मतलब स्पॉन्टेनियस प्रोसेस है. अगेन बी पॉइंट के लिए लिख सकता हूं, अगर स्पॉन्टेनियस प्रोसेस है, वी आर नॉट चेंजिंग टेम्परेचर प्रेशर, बी पॉइंट का टेम्परेचर प्रेशर फिक्स है, बट ये स्पॉन्टेनियस चेंज है तो डेल्टा जी नेगेटिव होगा. एंड डेल्टा जी वी कैन यूज दिस फॉर्मूला, डेल्टा जी इज इक्वल टू डेल्टा एच माइनस टी डेल्टा एस. टी डेल्टा एस should be negative. So from here I will get that entropy change will be positive or will be greater than delta H upon T. So this is also very common. अगर B पॉइंट पे उन्होंने रिलेशन पूछा तो हम कह सकते हैं एंट्रोपी चेंज की वैल्यू इससे बड़ी होगी क्योंकि ये इक्विलिब्रियम वाली वैल्यू है. और इफ दे आर आस्किंग एट सी पॉइंट, सी पॉइंट क्या है, H2O सॉलिड, प्रेशर 0.5 atm है, टेम्परेचर 273.15 केल्विन है. इस कंडीशन में सॉलिड स्टेट स्टेबल है, तो सॉलिड लिक्विड में कन्वर्ट ही नहीं होगा, इट इज नॉट गोइंग टू कन्वर्ट इनटू लिक्विड. सो व्हाट आई विल डू दैट, इफ आई कैलकुलेट डेल्टा जी एट दिस constant pressure and temperature, C point पे pressure temperature constant, I will say it is positive because reaction is non-spontaneous. So from here I can say that delta G is delta H minus T delta S. ये पॉजिटिव होना चाहिए. इसका मतलब है इंट्रोपी चेंज, अगर मैं इसको राइट हैंड साइड में ले जाऊं तो इंट्रोपी चेंज की वैल्यू डेल्टा H अपॉन T से कम आनी चाहिए. So these are very simple but very useful. They can ask question based on that, how to apply the concept of spontaneity in order to calculate the relation between entropy change and enthalpy change. Okay. Now try to solve this question. 1 mole of an ideal gas at 300 Kelvin in thermal contact with surrounding expands isothermally from 1 liter to 2 liter against a constant pressure of 3 atm. In this process the change in entropy of the surrounding, they are discussing about the surrounding. तो पहली बात तो ये है कि प्रोसेस आइसोथर्मल है, बट आइसोथर्मल इरिवर्सिबल है. आइसोथर्मल इरिवर्सिबल प्रोसेस इज देयर. अगर हमें सिस्टम की इंट्रोपी चेंज निकालना होता तो हमें कोई प्रॉब्लम नहीं थी, चाहे वो रिवर्सिबल हो या इरिवर्सिबल हो. इफ आई नो इनिशियल एंड फाइनल स्टेट आई कैन सॉल्व इट. But now we have to calculate the entropy change of the surrounding, and we have learned that entropy change of the surrounding is equal to Q surrounding upon temperature of the surrounding. और दे रखा है कि ये आइसोथर्मल प्रोसेस जो है वो कांटेक्ट सराउंडिंग के कांटेक्ट में है और वो टेम्परेचर उसका 300 केल्विन है, मतलब सराउंडिंग का टेम्परेचर भी 300 केल्विन है. So we know that what is the temperature of the surrounding, that is 300 Kelvin. अगर हम surrounding का Q कैलकुलेट कर लें तो हमारी प्रॉब्लम सॉल्व हो जाएगी. तो in order to calculate Q of the surrounding, what we are going to do, we are going to apply first law. First law में change in internal energy is equal to Q plus W. ये सिस्टम के लिए मैं लगा रहा हूं. सिस्टम आइडियल गैस है, टेम्परेचर कांस्टेंट है, इंटरनल एनर्जी का चेंज 0 होगा. सो फ्रॉम हियर आई कैन से दैट Q of the system is minus times of work done of the system. Work done calculate करना है irreversible process का. Work done in irreversible is minus times of P external, V final minus V initial. So this minus and minus will become plus. So this is Q system, P external into V final minus V initial. एक्सटर्नल प्रेशर दे रखा है 3 atm है और वॉल्यूम चेंज जो है वो 1 लीटर से 2 लीटर. सो दिस इज इन लीटर एटीएम. ये वैल्यू लीटर एटीएम में है. Now they have mentioned that 1 liter ATM is equal to 101.3 joule. So I can write that this is 3 into 101.3. So this is Q of the system. I know that Q of the system is minus times of Q of the surrounding because law of conservation of energy. अगर system heat energy ले रहा है तो surrounding provide कर रहा है और ये इसका reverse होगा. अगर work is done on the system means work is done by the system. Law of conservation of energy, right? So here I can get the value of Q and the Q will be negative. Q surrounding will be negative here and that is equal to minus 3 into 101.3. Now you can simplify this. This value is in joule, right? So if I am calculating this entropy change of the surrounding, entropy change of the surrounding is minus 3 into 101.3 divided by temperature. Temperature is 300. So simplify it. On simplification, we are getting 1.013. So this is the answer, right? इंट्रॉपी ऑफ द सिस्टम अगर हमें देखना है, क्योंकि हमें ये मालूम है कि यूनिवर्स की इंट्रॉपी बढ़ेगी, हम ऐसे देख सकते हैं कि in isothermal expansion system is gaining heat energy because internal energy is not changed. It is doing work. It is doing work because heat energy is given to the system, means heat energy is rejected by the surrounding. Q surrounding is negative, so entropy of the surrounding is going to decrease, right? A second example, so many type of processes are there and we have to calculate entropy change of system surrounding. So let me read the question. The first option is reversible condensation of vapor. Reversible condensation of vapor means I can take any vapor. I am taking water, so H2O in gaseous state, H2O in liquid state. This is condensation. Reversible word use किया है, मतलब वो ये कह रहे हैं कि this condensation is taking place at its condensation point. Reversible का मतलब ये है, right? So from there, I can write that entropy change is equal to delta H upon T. So entropy change in condensation is equal, because delta G is 0. So I can write delta H condensation divided by temperature. And delta H condensation, evaporation is endothermic, condensation is exothermic. So this is negative. Temperature in Kelvin is positive. So this whole thing is negative. Or if you know that entropy of gas is greater than entropy of liquid, from there also you can say that entropy of condensation is negative. For system, we have calculated that entropy change of the system is negative. If system is rejecting heat energy, who is going to get that? Surrounding is going to get that. With respect to surrounding, all the processes are reversible. Delta S surrounding is Q surrounding upon T. So Q surrounding is positive, temperature in Kelvin is positive. So this delta S surrounding will be positive. And since there is an equilibrium between system and surrounding, delta G of the system at constant temperature and pressure is equal to 0. Delta G of the system at constant temperature and pressure is minus T delta S total. Delta S total will be 0. So we can say that since it is reversible process, entropy of universe is not going to change. So decrease in entropy of system is equal to increase in entropy of the surrounding. So we can match it. For reversible condensation of vapor, we can say that delta S system will be negative and delta S surrounding will be positive. So there is no positive thing, right? So A का Q match होगा. Same way I can solve for B option. In B option, they are saying that irreversible adiabatic compression of an ideal gas. We have studied that any adiabatic process, delta S surrounding is not going to change because Q surrounding is 0. But since it is irreversible, in irreversible, we know that entropy of universe is going to be positive, and that can only be positive when entropy of system is positive. So we can say that for B, entropy of system is going to increase and there is no change in entropy of the surrounding. ऐसे ही अगर हम C option discuss करते हैं, isothermal free expansion in vacuum. So for free expansion, we know that work done will be 0 because P external is 0. एंड फ्रॉम एक्सपेरिमेंट, राइट, ये क्वेश्चन बार बार पूछा गया, मेंस में भी पूछा जा चुका है अब तो। फ्री एक्सपेंशन में फ्रॉम जूल्स एक्सपेरिमेंट, फ्रॉम एक्सपेरिमेंटली वी फाइंड आउट दैट देयर इज नो एक्सचेंज ऑफ हीट एनर्जी बिटवीन सिस्टम एंड सराउंडिंग। तो क्यू कैसे पता लगा? फ्री एक्सपेंशन में जूल्स एक्सपेरिमेंट की मदद से हमें पता चला, विद द हेल्प ऑफ, हमने एक्सपेरिमेंट किया और वहां से पता चला कि हीट एनर्जी का एक्सचेंज नहीं हो रहा है, तो क्यू इज इक्वल टू 0. So we know that there is no change in internal energy. Internal energy change नहीं होगा. Ideal gas के लिए internal energy change नहीं होगा, मतलब temperature constant होगा. अगर temperature constant है, ये एक तरह से isothermal irreversible process हो गया. If I have to calculate entropy change for ideal gas in any process, I can use delta S is equal to NCV ln T2 upon T1 plus NR ln V2 अपॉन V1. तो यहाँ टेम्परेचर चेंज नहीं हो रहा है, तो फर्स्ट टर्म 0 होना चाहिए, और V2 इज ग्रेटर देन V1 क्योंकि एक्सपेंशन हो रहा है, तो ये वैल्यू V2 इज ग्रेटर देन V1 मींस दिस इज पॉजिटिव. सो अगेन हियर दिस इज अ वेरी गुड एग्जांपल where the entropy of the system is going to increase. They can ask that what happens to the entropy of the surrounding in free expansion. In surrounding there is no exchange of heat energy, so Q surrounding is 0, so entropy of surrounding is 0. So what is about entropy of universe? Since it is irreversible process, entropy of universe is going to increase. So for the third option, isothermal, they have mentioned isothermal free expansion. If they have not mentioned isothermal word also, because in mains and advanced they have asked this question so many times, mentioned in NCERT that free expansion is an isothermal as well as adiabatic process. ठीक है, isothermal irreversible, adiabatic irreversible process है ये. So from here I can say that entropy of the system is going to increase and there is no change in entropy of the surrounding. And the last option is reversible adiabatic expansion. We have already discussed that रिवर्सिबल एडियाबेटिक मीन सिस्टम सराउंडिंग यूनिवर्स किसी की इंट्रॉपी चेंज नहीं होगी, सो इंट्रॉपी ऑफ द सराउंडिंग will change in entropy of the surrounding is equal to 0. Mixing of ideal gases at constant temperature and pressure. This topic is common in liquid solution as well as thermodynamics, and it's a very important topic. In NCERT, old NCERT, this diagram was given in solution. तो पहले ये NCERT में डायग्राम दे रखा था, इसलिए इसका रिवीजन ज्यादा जरूरी हो जाता है. तो सबसे पहले हम देख रहे हैं कि एक कंटेनर ए में एक गैस है, आइडियल गैस, जिसके नंबर ऑफ मोल्स Na, वॉल्यूम Va, प्रेशर P एंड टेम्परेचर T है. राइट हैंड साइड बी कंटेनर में गैस है जिसके नंबर ऑफ मोल्स B है, वॉल्यूम वॉल्यूम VB है और प्रेशर एंड टेम्परेचर सेम है. लेफ्ट हैंड साइड एंड राइट हैंड साइड गैस का प्रेशर टेम्परेचर सेम है. ये स्टॉप कॉर्क है, अगर मैं इसको रिमूव करूंगा तो मिक्सिंग होगी. जब मिक्सिंग होगी तो पूरे सिस्टम का पहले भी वॉल्यूम VA प्लस VB था, अभी भी वॉल्यूम VA प्लस VB है, तो कोई वॉल्यूम चेंज नहीं होगा, डेल्टा V मिक्सिंग विल बी 0. ठीक. नाउ since the temperature of both the gases will change, will same, so on removing this stopcock, temperature is also not going to change, and we know that enthalpy, internal energy change or enthalpy change of an ideal gas depends only on temperature. Temperature is not changing, so enthalpy change and internal energy change for ideal gas is equal to 0. Now entropy change की बात करते हैं. क्या हो रहा है कि जब गैस A पहले केवल VA वॉल्यूम में थी, जब हमने स्टॉप कॉर्क को खोल दिया तो अब ये VA प्लस VB वॉल्यूम में है, दोनों में है. यहाँ से वी आर रिमूविंग दिस स्टॉप कॉर्क, यहाँ ये होना नहीं चाहिए, शुड नॉट बी हियर. सो व्हाट वी आर डिस्कसिंग दैट अब वॉल्यूम VA प्लस VB हो गया, पार्शियल प्रेशर गैस का चेंज हो रहा है लेकिन टोटल प्रेशर सेम है, PA प्लस PB की वैल्यू P के बराबर है. So now partial pressure is changing, but total pressure remains same for the whole system. Entropy change for gas A, I can write NCV ln T2 upon T1. T1, T2 is same, so that is 0. NAR ln V final upon V initial. V final, VA को मैं लिख सकता हूँ N, VA की वैल्यू यहाँ से NA RT upon P, and VB की वैल्यू हो सकती है NB RT upon P. इन द डिनोमिनेटर VA इज NART, RT अपॉन P ऊपर और नीचे कॉमन है तो कैंसिल आउट हो जाएगा। मैं इसको इस तरह से लिख सकता हूँ और इसको फर्दर सिंप्लीफाई कर सकता हूँ। इंट्रोपी चेंज ऑफ गैस A विल बी पॉजिटिव, दैट इज NAR ln XA। XA की वैल्यू 1 से कम है तो ये नेगेटिव और नेगेटिव पॉजिटिव हो जाएगा। तो ऑब्वियसली ए गैस की इंट्रोपी बढ़ेगी क्योंकि गैस की फ्रीडम बढ़ रही है। पहले ये ए कंटेनर में ही थी, अब ए और बी दोनों में है, और बी के लिए भी ऐसा ही होगा, तो दोनों गैसेस की इंट्रोपी बढ़ेगी। इसलिए डेल्टा एस मिक्सिंग इज पॉजिटिव, क्योंकि ये इरिवर्सिबल प्रोसेस है। जैसे इसको स्टॉप कॉक को खोलोगे दोनों गैसेस मिक्स हो जाएंगी। इरिवर्सिबल प्रोसेसेस जो होते हैं उसमें यूनिवर्स की इंट्रोपी बढ़ती है। सराउंडिंग का क्या है, जब हम ये प्रोसेस कर रहे हैं तो पूरे सिस्टम का वॉल्यूम कांस्टेंट है। मैं एक गैस की बात नहीं कर रहा हूँ, पूरे सिस्टम का वॉल्यूम कांस्टेंट है। इसका मतलब वर्क डन पूरे सिस्टम के लिए 0 होगा। और चेंज इन इंटरनल एनर्जी हमने देख लिया, क्योंकि टेम्परेचर सेम है तो डेल्टा यू 0 होगा पूरे सिस्टम के लिए। सो डेल्टा यू इज इक्वल टू क्यू प्लस डब्ल्यू। वर्क डन 0 है, डेल्टा यू 0 है तो क्यू 0 होगा। देयर इज नो एक्सचेंज ऑफ हीट एनर्जी इन दिस प्रोसेस व्हेन मिक्सिंग इज टेकिंग प्लेस, राइट? So we can say here that डेल्टा एस सराउंडिंग, अगर हम सराउंडिंग के एंट्रोपी की बात करें तो डेल्टा एस सराउंडिंग विल बी 0 because there is no exchange of heat energy between system and surrounding. And delta G is delta H minus T delta S. Delta H mixing is 0 and delta S mixing is positive. From there we'll get that delta G mixing will be negative. It is not 0, this is negative. Delta G mixing is negative. And if I draw energy versus mole fraction graph for this whole system at different composition, means there are infinite number of compositions, means we have taken infinite number of system and then we have drawn this graph. While drawing this graph, we have kept that number of moles of A plus number of moles of B is constant. A plus B के number of moles constant है. And then we are drawing this graph. So we know that with different composition, right, this is the variation of Gibbs free energy, and the change in Gibbs free energy will be minimum when the mole fraction of A is equal to the mole fraction of B, right? You can prove with the help of this equation. You are going to prove it. I'm not proving, I'm just telling that. यहाँ पे कई बार ये ग्राफ्स दे रखे होते हैं और यहाँ कई ग्राफ्स में ये टेम्परेचर होता नहीं है। इंट्रोपी इज नॉट एनर्जी, इंट्रोपी इज Q upon T. So be careful about that. T delta S is sign of energy. Delta S is positive. Temperature in Kelvin is positive. So this is the graph. Entropy of mixing will be maximum here. So that's why this is maxima here, right? And this is maximum when equal number of moles of both gases are mixed. जैसे अगर हमारे पास टोटल 10 मोल है, एक कंडीशन हो गई कि ए गैस का 1 मोल है, बी का 9 है, और एक कंडीशन 2 8 और एक कंडीशन 5 5, तो जब हम इन दोनों के 5 5 मोल मिक्स करेंगे तो इंट्रोपी चेंज ऑफ मिक्सिंग विल बी मैक्सिमम. सो दिस इज वेरी इंपॉर्टेंट. मिक्सिंग में सिस्टम की इंट्रोपी बढ़ेगी, सराउंडिंग की इंट्रोपी में कोई चेंज नहीं होगा. देयर इज नो चेंज इन डेल्टा एच डेल्टा यू ऑफ द सिस्टम. द गिब्स फ्री एनर्जी ऑफ द सिस्टम इज गोइंग टू डिक्रीज. ये लास्ट ईयर जेई मेंस में ये क्वेश्चन पूछा गया, बट ये बहुत सालों से हम पढ़ा रहे थे. तो लेट अस डिस्कस दिस क्वेश्चन, राइट? देयर आर सम इंपॉर्टेंट पॉइंट्स आल्सो. लेट अस डिस्कस. When two equal size pieces of same metal at different temperature, T hot and T cold, are brought into thermal contact and isolated from surrounding, the total change in entropy of the system is given by, we have to calculate what is the total change in entropy. तो सॉल्व करने से पहले अगर हम लॉजिक लगाएं तो एक बॉडी जो है वो हॉट है, एक का टेम्परेचर ज्यादा है, दूसरी बॉडी कोल्ड है, उसका टेम्परेचर कम है, और ये दोनों बॉडीज एक दूसरे के कांटेक्ट में है. सो ऑब्वियसली हीट एनर्जी विल फ्लो फ्रॉम हायर टेम्परेचर टू लोअर temperature. It is a spontaneous process, and we know that in a spontaneous process the entropy of universe is going to increase. So already हमें result पता है. Since it is isolated from its surrounding, so Q surrounding is equal to 0. There is no exchange of heat energy between system and surrounding. तो वहां से हम कह सकते हैं डेल्टा एस सराउंडिंग इज इक्वल टू 0. और हमें पता है कि ये स्पॉन्टेनियस प्रोसेस है. डेल्टा जी नेगेटिव मतलब डेल्टा एस टोटल पॉजिटिव, डेल्टा एस टोटल वैल्यू पॉजिटिव, मतलब डेल्टा एस सिस्टम की वैल्यू जो है वो पॉजिटिव ही आएगी. इंट्रोपी ऑफ सिस्टम इज गोइंग टू इंक्रीज. सो हियर मैथमेटिकली वी हैव टू कैलकुलेट. सो व्हाट वी कैन डू दैट, अभी ये इक्वल साइज है और सेम मेटल है, तो अगर इसका मास m है, इसकी स्पेसिफिक हीट कैपेसिटी s है, इसका मास भी m होगा और इसकी स्पेसिफिक हीट कैपेसिटी भी s होगी। तो हीट लॉस इज इक्वल टू हीट गेन। सो वी कैन राइट दैट ms फाइनल टेम्परेचर को T मान लेते हैं और इनिशियल टेम्परेचर T हॉट। सो दिस इज लॉस ऑफ एनर्जी प्लस gain of energy, that is ms, final temperature is T, initial temperature is T cold, नेट एनर्जी का एक्सचेंज जीरो, ये लॉस लूज करेगा और ये गेन करेगा, राइट, बट नेट एनर्जी विल बी रिमेन सेम, राइट। सो दिस इज इक्वल टू जीरो। सो if I simplify from here, I can write that temperature final is equal to T hot plus T cold divided by 2, ये final temperature हो गया। Now what we are discussing here कि एक मेटल का जो है वो कूलिंग इफेक्ट हो रहा है, मेटल का टेम्परेचर धीरे धीरे डिक्रीज हो रहा है और मेटल ये धीरे धीरे नहीं हो रहा होगा, बट वी हैव डिस्कस्ड दैट कि इफ इनिशियल एंड फाइनल स्टेट इज सेम, इंट्रोपी चेंज विल बी सेम। सो दैट्स व्हाई मैं इसको धीरे धीरे मान के इंट्रोपी चेंज कैलकुलेट कर रहा हूं। तो एक का टेम्परेचर बढ़ेगा, दूसरे का घटेगा, और ये सॉलिड है। तो इंट्रोपी का फॉर्मूला तो बेसिक हम लगाएंगे, ds इज इक्वल टू डेल क्यू रिवर्सिबल अपॉन टेम्परेचर, और सॉलिड है और ये सब कुछ जो है कांस्टेंट प्रेशर पे हो रहा होगा, तो डी क्यू पी रखेंगे, डी क्यू पी इज इक्वल टू एन इंटू सी पी इंटू डी टी अपॉन टी। तो एक लिक्विड, एक सॉलिड के लिए, इस मेटल के जिसका टेम्परेचर डिक्रीज कर रहा है, मैं अगर इंटीग्रेट करूं तो ये हो गया डेल्टा एस इज इक्वल टू एन सी पी इज कॉन्स्टेंट, सो आई कैन राइट एन सी पी लॉन टी फाइनल, टी फाइनल हो गया टी हॉट प्लस टी कोल्ड डिवाइडेड बाई 2 एंड टी इनिशियल वॉज टी हॉट। ये हो गया इंट्रोपी चेंज, राइट। सेम वे आई कैन कैलकुलेट इंट्रोपी चेंज फॉर द कोल्ड पार्ट। कोल्ड पार्ट के लिए भी मैं यही लिख सकता हूं, दैट इज इक्वल टू एन इंटू सी पी लॉन फाइनल टेम्परेचर इज टी हॉट प्लस टी कोल्ड डिवाइडेड बाई 2 एंड इनिशियल टेम्परेचर वॉज टी कोल्ड। सो इफ आई एड दीज टू, क्योंकि हमें पता है कि अगर हम इन दोनों को ऐड करेंगे, एन इंटू सी पी की वैल्यू, सेम मास सेम मेटल, राइट, तो ये वैल्यू सेम होगी। तो इफ आई ऐड, आई कैन राइट दिस एज एन सी पी तो हो गया कॉमन, इसको लिख सकते हैं हम टी हॉट प्लस टी कोल्ड होल स्क्वायर डिवाइडेड बाई 4 टाइम्स ऑफ टी हॉट प्लस टी कोल्ड, राइट। सो दिस इज द एंट्रोपी चेंज ऑफ द सिस्टम एंड दैट शुड बी पॉजिटिव, राइट। तो ये आंसर होना चाहिए, डी ऑप्शन होना चाहिए। एन इंटू सी पी को लिखा उन्होंने हीट कैपेसिटी कैपिटल सी से डिनोट कर दिया, सो डी विल बी द आंसर। So this question was there from long, many years we are doing the same question, but last year they have asked this question, but again they can ask about these information, that what is about entropy change of surrounding and what is about entropy change of universe। और ये लास्ट क्वेश्चन डिस्कस करते हैं एंट्रोपी चेंज से रिलेटेड, मैच द कॉलम, जेई एडवांस का क्वेश्चन है, बट इसमें बहुत सारे कॉन्सेप्ट्स कवर हो जाएंगे। तो पहला है CO2 इन सॉलिड स्टेट टू CO2 इन गैसियस स्टेट। तो कई बच्चों को ये कंफ्यूजन होता है कि ये फेज ट्रांसफॉर्मेशन, फेज ट्रांजिशन है या नहीं है। सब्लिमेशन है, ये सबको पता है। फेज ट्रांजिशन, सब्लिमेशन, राइट। फेज ट्रांजिशन जो है उसमें फॉर्मूला चेंज नहीं होना चाहिए। तो अभी अगर देखें तो CO2 सॉलिड, CO2 तो लेफ्ट एंड राइट में फॉर्मूला सेम है, तो हम ये कहेंगे दिस इज फेज ट्रांजिशन। ये फेज ट्रांजिशन तो हम कहेंगे क्योंकि फॉर्मूला चेंज नहीं हो रहा है। और सॉलिड से गैस में जाना मतलब सब्लिमेशन, मतलब एंडोथर्मिक प्रोसेस मींस इंथैल्पी चेंज विल बी पॉजिटिव, इंथैल्पी चेंज पॉजिटिव होगा। इंट्रोपी चेंज अगेन सॉलिड से गैस में जा रहा है, राइट, तो इंट्रोपी चेंज भी पॉजिटिव होगा, तो इंट्रोपी चेंज विल बी पॉजिटिव। व्हाट इज डेल्टा एस इज नेगेटिव, दैट इज रॉन्ग। सो इसका पहले का तो हो गया, पहले का आंसर होगा पी आर एंड एस। तो इसमें हमने सीखा कि अगर फॉर्मूला चेंज नहीं होगा तो उसको फेज ट्रांसफॉर्मेशन कहेंगे। अभी दूसरा क्वेश्चन है, इसमें फॉर्मूला चेंज हो रहा है, ये केमिकल रिएक्शन है, सो इट इज नॉट अ फेज ट्रांजिशन, इट इज अ केमिकल रिएक्शन, क्योंकि लेफ्ट हैंड साइड राइट हैंड साइड में फॉर्मूला अलग अलग है। तो अभी इसमें फेज ट्रांजिशन नहीं है। एलोट्रोपिक चेंज, एलोट्रोपिक चेंज का क्या मतलब है? अगर मैं ये कहता हूं कि एलोट्रोप वर्ड जो है वो कंपाउंड्स के लिए यूज नहीं होता, allotrope is used for element only, it is used for element। और अगर किसी एलिमेंट की कोई फॉर्म है जिसमें एलिमेंट अलग अलग तरह से कंबाइंड है, जैसे कि मैं ये कह रहा हूं कि ऑक्सीजन और ओजोन, ये एलोट्रोपिक फॉर्म है। दिस इज एलोट्रोपिक फॉर्म, क्योंकि ऑक्सीजन में ऑक्सीजन डबल बॉन्ड ऑक्सीजन है, ओजोन में इसका कॉम्बिनेशन थोड़ा डिफरेंट है। दिस इज द स्ट्रक्चर। तो ऑक्सीजन एटम अलग अलग तरीके से जुड़े हुए हैं, इसलिए ये एलिमेंट है, अलग अलग तरीके से जुड़े हुए हैं, तो ये एलोट्रोप है। मैं ये नहीं कहूंगा कि नेसेंट ऑक्सीजन एलोट्रोप है, बिकॉज नेसेंट ऑक्सीजन में कोई कॉम्बिनेशन नहीं, अकेला ऑक्सीजन एटम है। तो व्हेन वी आर सेइंग द सब्सटेंस इज एग्जिस्टिंग इन लिक्विड एंड गैस स्टेट, विल सी लाइक दैट। अगर वो सॉलिड है तो उसके डिफरेंट क्रिस्टलाइन स्ट्रक्चर्स होने चाहिए। जैसे अगर मैं ये कहता हूं कि सल्फर है, सल्फर एसिड सॉलिड स्टेट में ऑर्थोरोम्बिक फॉर्म है, या सल्फर एसिड सॉलिड स्टेट में मोनोक्लिनिक फॉर्म है, इनके क्रिस्टलाइन स्ट्रक्चर अलग अलग है। अभी हमने सॉलिड स्टेट पढ़ा था, उसमें ऑर्थो मतलब माचिस का डब्बा, मतलब ऑल द थ्री साइड्स आर डिफरेंट, ऑल द थ्री एंगल्स आर इक्वल टू 90 डिग्री। मोनोक्लिनिक में पहली बार दो एंगल जो हैं अल्फा और गामा 90 के बराबर थे, बाकी ए इज नॉट इक्वल टू बी इज नॉट इक्वल, सो देयर क्रिस्टलाइन स्ट्रक्चर इज डिफरेंट। सो यहाँ पे मतलब जिस तरह से सल्फर एटम जुड़े होंगे वो डिफरेंट होंगे। So because of that, these are allotropes, right? They are elements existing in two different crystalline forms, so they are allotropes. So allotropes के formula same भी हो सकते हैं, allotropes के formula different भी हो सकते हैं, right? So here when we are discussing मतलब इसमें ये इस gaseous वाले की बात कर रहा हूँ, अगर कहीं कोई क्वेश्चन आता है कि allotropes में, तो उनके formula same भी हो सकते हैं, formula different भी हो सकते हैं। Now let us discuss this second part, that calcium carbonate in solid state, break कर रहा हूं मैं, तो it is an endothermic process. If it is an endothermic process, so I have to give heat energy, delta H will be positive, or we can say that delta Ng for this chemical reaction, delta Ng right hand side में गैस के पार्टिकल है, लेफ्ट में है ही नहीं, तो इंट्रोपी बढ़ेगी। अब मैं ये भी सोच सकता हूँ हीट एनर्जी दे रहे हैं, Q upon T will be positive, so entropy change will be positive for this, so R and S। एलोट्रोपिक चेंज है नहीं, फेस ट्रांसफॉर्मेशन है नहीं। एलोट्रोपिक वर्ड किसके लिए यूज होता है? एलिमेंट के लिए यूज होता है। नाउ ये सबसे इंपॉर्टेंट है, इसमें पहली चीज तो है कि फॉर्मूला चेंज हो रहा है, तो ये फिजिकल प्रोसेस तो हुआ नहीं, फेस ट्रांसफॉर्मेशन नहीं है, ये केमिकल रिएक्शन है, तो फेस ट्रांसफॉर्मेशन नहीं है। ये एलोट्रोप्स नहीं है, क्योंकि एलोट्रोप्स O2 और O3 एलोट्रोप्स हैं, यहाँ पे अलग तरीके से ऑक्सीजन कंबाइन है, लेकिन हाइड्रोजन नेसेंट फॉर्म में कोई कॉम्बिनेशन ही नहीं है, तो ये एलोट्रोपिक फॉर्म नहीं है। एलोट्रोप एलिमेंट के लिए यूज होता है, बट नेसेंट फॉर्म जो होता है एटम का, वो एलोट्रोपिक फॉर्म नहीं होता। थर्ड, अगर हम दो गैस को मिला के एक मॉलिक्यूल बना रहे हैं तो बॉन्ड बनेगा, एनर्जी रिलीज होगी, सो दिस डेल्टा एच शुड बी पॉजिटिव, डेल्टा एच पॉजिटिव, तो डेल्टा एस भी पॉजिटिव होना चाहिए। मतलब इस प्रोसेस में गैस के मोल्स कम हो रहे हैं, तो सिस्टम की इंट्रोपी डिक्रीज करेगी, डेल्टा एस इज नेगेटिव। So I think you got the point, allotropic form, right? And phase transformation, यहाँ फॉर्मूला चेंज हो रहा है तो फेस ट्रांसफॉर्मेशन नहीं है, नेसेंट हाइड्रोजन है तो एलोट्रोपिक फॉर्म नहीं है। एंड दिस इज व्हाइट फॉस्फोरस टू रेड फॉस्फोरस। डी को डिस्कस करते हैं इन डी ऑप्शन। व्हेन वी आर सेइंग व्हाइट फॉस्फोरस इज मॉलिक्यूलर सॉलिड, वेंडरवाल फोर्स ऑफ अट्रैक्शन होता है इस सॉलिड में, राइट? व्हाइट फॉस्फोरस इज वेरी रिएक्टिव एंड मॉलिक्यूलर सॉलिड, ये हो गया। रेड फॉस्फोरस इज अ पॉलीमर, ये इसका पॉलीमर होगा, राइट? रेड फॉस्फोरस में एक P4 मॉलिक्यूल और दूसरा P4 जो मॉलिक्यूल है, एक तरह का कोवलेंट सॉलिड हो गया। एक मॉलिक्यूल और दूसरे मॉलिक्यूल के बीच में, दो फॉर्मूले के बीच में कोवलेंट बॉन्ड है, सो क्रिस्टलाइन स्ट्रक्चर इज डिफरेंट हियर। फॉर्मूला P लिखा है, यहाँ भी P लिखा है, तो फेस ट्रांसफॉर्मेशन तो हो गया। एलोट्रोप, यस एलोट्रोपिक चेंज है। एलोट्रोप वर्ड इज यूज्ड फॉर एलिमेंट्स, एलिमेंट्स हैं ये, और दोनों के फॉर्म्स क्रिस्टलाइन फॉर्म्स अलग अलग हैं, तो दिस इज एलोट्रोपिक फॉर्म। डेल्टा एच, यहाँ पे बच्चे गलती करते हैं, तो देखो क्योंकि हम इनऑर्गेनिक केमिस्ट्री में पढ़ते हैं कि वन ऑफ द मेथड टू कैलकुलेट व्हाइट फॉस्फोरस टू रेड फॉस्फोरस, अगर हमें व्हाइट फॉस्फोरस से रेड फॉस्फोरस बनाना है तो हम उसको हीट करते हैं। ये बात सही है कि हम 2-3 दिनों तक हीट करते हैं तो व्हाइट फॉस्फोरस रेड फॉस्फोरस में कन्वर्ट हो जाता है, लेकिन हम हीट इसलिए करते हैं कि पुराने बॉन्ड ब्रेक कर जाए व्हाइट फॉस्फोरस के, और वो वीक होते हैं ये वाले, क्योंकि स्ट्रेन है काफी 60 डिग्री एंगल की वजह से, तो हीट करने पे ये पुराने टूटते हैं और नए फॉर्म होते हैं। ये वाले जो नए फॉर्म हुए ये ज्यादा स्ट्रांग है। तो वी कैन से दैट एक लॉजिक तो ये हो गया कि दो चीजें हो रही हैं, केवल हमें ये नहीं देखना है कि हम हीट करते हैं, हीट करते इसलिए क्योंकि पुराने बॉन्ड ब्रेक हो और नए बॉन्ड जो बनेंगे ज्यादा स्टेबल है तो ज्यादा एनर्जी रिलीज होगी, तो ओवरऑल रिएक्शन, ये जो रिएक्शन है वो एक्सोथर्मिक है। दिस इज एक्सोथर्मिक रिएक्शन, राइट? ये दूसरा तरीका बड़ा सिंपल है कि ये जो व्हाइट फास्फोरस है ये मोनोमेरिक फॉर्म में, वेंडरवाल फोर्सेस हैं, ये एन मॉलिक्यूल्स जब इसके कंबाइन होंगे तो ये बनेगा पॉलीमर। तो कॉम्बिनेशन हो रहा है, बहुत सारे मॉलिक्यूल्स कंबाइन हो रहे हैं, तो उसमें इंट्रोपी क्या करेगी, डिक्रीज करेगी, राइट। सो कई बच्चों ने इसको जो है इनऑर्गेनिक में पढ़ रखा है कि हम हीट करते हैं इसलिए उन्होंने लिखा है डेल्टा एच पॉजिटिव, जो कि गलत है। तो फेस ट्रांसफॉर्मेशन है, एलोट्रोपिक चेंज है, और इंट्रोपी चेंज इज नेगेटिव। दिस इज द आंसर, राइट। सो दिस इज ऑल्सो वेरी इंपॉर्टेंट। सो आई होप बाई डिस्कसिंग दिस many concepts have been clear regarding thermodynamics। तो दोस्तों मैंने कोशिश करी है थर्मोडायनेमिक पार्ट 1 में कि आपको इंटरनल एनर्जी, इंथैल्पी और इंट्रॉपी के बारे में नॉलेज हो जाए, कैसे अप्लाई करना है क्वेश्चंस में, कोई गलती नहीं करनी है, इसकी हमने कोशिश करी है। अगर आपको हमारा वीडियो पसंद आ रहा है तो प्लीज़ इस लाइक करें, और अगर आपके फ्रेंड्स वगैरह हैं तो उनको बताएं कि ये चैनल है, इसको सब्सक्राइब करें। थैंक यू।